Okay, so I'm using a different software here for my writing. So we'll see how it goes. Okay, so let's just review what we did last time, just in case. So we finally reached the point of the key point of the course, and that's the definition of a limit. Okay, where's the... Okay, so it doesn't look too bad. We'll need to make it thicker. You make it fixed. Okay. Okay. Okay, so what we did was the idea is so given a sequence AN, okay, well, let's not try to figure out what it means anymore. Let's suppose we already understand what sequences are, and we have a bunch of examples, and we're looking at all sequences here, all the sequences at the same time. Okay, so and then what is a limit? Its limit is a number to begin with, number, say L. And as it is always often done in mathematics, it is the definition are based on description of the property that is to be satisfied. This number has to satisfy it, rather than specifically pointing out what it is. Okay, so well, and that's the tricky part. Okay, so so this is how it is given given a sequence for any as I described it last time, a degree of accuracy epsilon, we can point to a place in the sequence such that all entries past that point are within epsilon from L. Okay, so if we put n's here and an y on the y-axis, this is my L. Okay, so then what I'm saying here is my sequence might start large. It doesn't matter. It might start large, but sooner or later it has to be within that band. Okay, the band, we have to say that the entries are within epsilon from L means that they fit this band. Let me try to do it like this. So suppose this width of this marker is epsilon. Okay, so the tail of my sequence has to fit within this band. Okay, so once again, this is my L over here, and then I step up and down by epsilon. Okay, and the sequence has to, and that's what I'm drawing here in red, the sequence itself, it is eventually ends up entirely within this band. Okay, so that's what we're saying, that the limit it is. So is of the sequence is equal to L. So notation is an arrow L as an arrow infinity. Okay, so once again, the language is an, either you say L is the limit of an, or you say an converges to L and then goes to infinity and so on. Okay, so so in addition to the examples that we had before, let me let me review one again one more time. Where is it? So once again, that example, that is the standard and most basic. Let's modify it slightly. 1 over n squared. Okay, so the limit is, once again, this is the definition, a very precise way of thinking about things. But for computations, we have to develop all kinds of intuitions and clues to understand what the answer is. So we considered 1 over n last time. This time we're looking at 1 over n squared. So what's the difference? Not a big deal. They're actually, in fact, similar. In what sense? The numerator is 1, denominator is n, yesterday n squared. Today, in either case, denominator itself goes to infinity. Okay, so, and then this is one of the clues we have to pick up, is that when you divide a fixed number by a number that goes to infinity, the whole thing goes to what?
0.
To 0, right? Okay, so every time that will repeat itself. So it's we'll have, every time we have a fraction, what we're going to do, we're going to compare numerator with the denominator, and we'll see which one is larger at the infinity as we keep developing. Okay, so as we're going, when it is 1 in the numerator, or any number, I could put 1 million there, it wouldn't make any difference, because at some point n squared will overcome that million by any proportion imaginable, and that's why ultimately it will overcome it and push the whole thing, the whole fraction, down to 0. Okay, so that's how we're gonna guess answers, what the limit is. That's how. And we'll develop more, but at this time I just want to take this informal definition and carry it out just once, as we did before. So I'm given epsilon. In what sense given? We say epsilon is given. We just say that it is an arbitrary. So epsilon greater than 0 is arbitrary. Okay, arbitrarily small. Arbitrarily small. So once again, your boss comes to you and tells you, this is the accuracy I want, and you should be able to provide it instantly. And then we want to have 1 over n squared minus 0. That's the distance from 1 over n and 1 over n and 0. This is, we take the difference, should be less than epsilon. And then just like we did it last time, we do a little algebra. We discover that, what is it? 1 less than epsilon n squared, or furthermore n squared larger than 1 over epsilon, and furthermore n larger than 1 over square root of epsilon. Okay? So that is when we're talking about point to a place in the sequence such that all entries past that point are within epsilon from L. That's exactly what we have. If we pick, this is the point, past this n, all an are within epsilon from 0. Okay, so you don't have to look at the picture. Pictures might be deceiving, but this is the algebra indicates that we are able to handle it. And this is a lesson of how to handle infinities. So remember, yesterday we did what happens if you were very casually treat infinities. You might run into trouble. So as a caution, before we do algebra with any kind of sequence, we want to make sure that it is convergent. There is a number L somewhere. Okay. So how do we deal with a sequence that has infinitely many entries? That's how. Okay, so as long as the sequence itself is fairly simple, we can it's not going to be any harder than that. So it's a very short computation, solving an inequality. That's what it amounts to. And once again, we're pointing out that that 1 over epsilon, 1 over square root of epsilon might be large. Imagine that if epsilon is a very large number, a very small number, that's the accuracy required, then n, the cutting point of somewhere here, say, in my sequence, might be very far to the right, but we don't care because we have no matter how far off we cut it, there are still infinitely many left. Okay, so and that's the infinity part of the sequence that we care about. Okay, so that's how it works out. Secondly, the other example we had was an is equal to -1 to the n, which alternates between 1 and -1, and the answer was, as you recall, no limit. We say no limit. What has happened? That's the consequence of the definition of a new concept by means of a property. A property is supposed to satisfy. So the properties, you say, well, this thing satisfies this property, but we don't know ahead of time whether there is such a thing that satisfies this property. Okay, so it's a number that satisfies a particular property. For example, x squared is equal to -1. Is there such a real number in nature? And no. So we describe a number by property, and then we might discover that there is no such number. That's exactly the same thing happened with limits. We describe roughly what I have here, what that number is supposed to be like, and then we might discover that there is no such number. And that's the example. I cannot, the difficulty here is that we are proving the negative, so we don't really know where that number, we cannot pick a specific number. We have to prove it for every L imaginable. And fortunately, it's not too bad. I choose the accuracy equal to 1/2, and then we observe that this sequence won't fit into a band of width 1. Okay, so just like over there, we chose epsilon to be equal to 1. The width is, I'm sorry, 1/2. The width of the band is 1, but the swing of the sequence is 2, because it swings by 2 at a time, and it keeps going on into infinity. It keeps doing exactly the same thing. There is no diminishing of the swing. Okay, so that's the proof that there is no such number. So that's the proof. So conclude, -1 to the n diverges. Okay, so that's the language. Let me state the definition. Okay, how do we page Ed? Okay, here it is. Okay, so the definition itself should be written at least once. So we say that, well, what happened? Wait a minute, I had lining, now I don't have lining. Rules. Okay, well, uncomplicated. So we say that sequence AN converges to L, its limit, and write AN arrow L if for any epsilon greater than 0 there is an n, an integer n, such that AN minus L is less than epsilon. Okay, so that is just the algebraically translate the language that we have over here. The sequence beyond some point that we have found is within epsilon from L. That's this inequality over here. So AN is within epsilon from L. Okay, so some geometric description is turned into a description which is purely algebraic. So if there is no such number L, we say that AN diverges. Frequently putting braces around these is better. Okay, then you literally, so there is no, you don't say it is equal to something. you simply write, you just write words, it is diverges. Also another notation is that is most common is LIM. So AN is equal to L, n goes to infinity. Shit, what is that thing? Eraser. As n goes to infinity, so you point it out. And if it exists, otherwise you can say, when there is divergence, you say that limit does not exist. Okay, so we use limits throughout calculus. It is the cornerstone of calculus for studying everything imaginable. Wherever infinitely long processes are involved, or we're talking about infinitely large numbers informally, or we speak of infinitely small numbers, that's always behind it, always the same thing. Okay, so one thing that is very prominent elsewhere, that's the decimals. Infinite decimals. What's the meaning of an infinite decimal? You cannot understand it in any other way but as limits. So when you have finitely many decimals, we know it's just a fraction. You have infinitely many, it is in fact a sequence of convergent sequence of numbers. So I did 999, but it just as well 0.8, 0.85, 0.858, 0.8585. It doesn't matter. It is a sequence, and it is. If we put it together, it becomes infinite decimal fraction with alternating digits. 8585 being repeated. Or you might remember this notation with a bar above. But it is in fact there are infinitely many terms. What is the meaning of this number? This is the limit of the sequence IAN, which is this. Okay, so one example outside of calculus technically is the decimal representations of real numbers, and that's how it appears. Transcendental numbers don't have repeating pieces like this, and they still are subject to the same definition. Okay, so definition. So let's look at some algebra. Well, actually, beforehand, I already addressed one issue, and that issue is something is defined and through a property that is to be satisfied, which means that there might be no such number, which is this is the example. Another possibility, can you think of another problem that might appear? You describe some concept with the property. One bad possibility if there is no such a number. On the opposite end of this, what could happen? None is bad. Okay, there is no such number.
Every number?
What?
Every number works?
Well, every number or just more than one. I mean, if you speak of the limit, and didn't I? Well, I think I did, I was careful. I put its. You see over here, I put its instead of, which is naturally would be to say the limit, and it is you will keep referring to this to that number is the limit of the sequence. But if it is described with a property, hypothetically there might be more than one number satisfying this. Okay, so hypothetically ahead of time we don't know that's the case. Fortunately, it is the case. It requires the proof. You can certainly find it in sources if you care, but let's just so I want to state it. in the form of a theorem. Is it thick enough to read? Okay. So there can be only one limit for a given sequence. So it is always either one or none. So we have divergent sequences. They're bad. We just try to stay away from them because we really cannot do anything with them. Limit is a meaningless concept, or it is a meaningless number. It's not a number. At the same time, there can be two. It also would be bad if there were two limits. Once again, you don't know which one is the one we're doing algebra with. But fortunately, there can be only one such a thing. You can certainly, if you give it some thought, you can see why. So if I have two candidates, this is L1 and this is L2, and then the tail of my sequence has to fit around one. It has to fit around this one on one hand, and on the other hand, it's also supposed to fit in around the other one like this. So the tail of the sequence has to be within the yellow band, and at the same time it would have to be within the, what's this color? Blue. Okay, let's call it blue. Blue color. Okay, so, and which is impossible because they don't overlap. So the sequence either will be wildly running up and down without limit, or it would have to be, it cannot contain, or will be containing one or the other, but not both. Okay, so the tail cannot end up, even though you might looking like this, might suggest that it's not the whole tail. It will be still jumping up and down without end. Okay, so that's roughly the proof by contradiction. Well, that's what that picture that I have justifies how it works out. So you assume that there are two limits. Is it possible that they are? And if they are distinct, we can also split the sequence between the two, and that's how we arrive to a contradiction. So in that sense, we are on a firm ground. It takes some effort to prove this statement, but otherwise we'll just take it on faith. Okay, so let's take some limits that are, again, there is no lining. Okay. Let's take simple examples of sequences, the one that we have seen already. So examples, and try to come up with some patterns. Okay, so what is the simplest sequence?
The same number repeating itself.
Right. Yeah. Is a constant one. Say an is equal to a for all n. Okay, so what do you think happens to this limit? It is equal to a, so limit an is equal to a as well. It certainly stands to reason that it's not going anywhere to the first place, so there is even no accumulation, which the examples that we have seen, there's accumulation, gradual accumulation of numbers from of the sequence towards the limit. In this particular case, they're simply not going anywhere to begin with, and if you take the definition, what you're supposed to write here, an minus a, is it less than epsilon? Well, of course it is, because it is a minus a, which is 0, and of course it is less than epsilon. So yes. Okay, so just to verify the definition quickly, this is the outcome. So that's one. Another slightly more complicated example from recently, from last week, is an arithmetic progression. Remember what that is. It is if you need to remember it is about it's like repeated deposits. What? Plus 2, yeah. So you keep adding the same number. So like 100 plus 100 plus 100, like this. So that's how you would describe the process of adding $100 to your bank account. So you add plus, plus, plus. Fortunately, we have a sequence. We can describe it in a more consistent way. So how about a naught plus n times, well, let me start over. I'm gonna make this stick. View. Duck. No, that's not it. Maybe, nope, that's not it. That's not it. And now I don't know how to, okay, here it is. Okay, the ribbon, how to fix the ribbon to the, so it wouldn't do this.
Zoom out.
Am I seeing, what?
Zoom out, maybe?
No, zoom out will be just the increasing the page bigger if you want larger numbers, but there is a, shoot. Desktop, rule lines, just, damn it. Add rule lines. Emphasize zoom in, 100, new window, new, no. Maybe options. Come on. Okay, that thing is also very slow. They still need to. There's settings somewhere. Shoot. Right click. That should work, but it never does. We'll disappear eventually. Anyway, so I'll have to do that. Okay, what happened? No. Okay. So what happened? Okay. Okay. So razor. Okay. So what I'm going to do is add m every time. So start with say b, and then add m every time. Okay, so what's going to be? It's going to be then an plus 1 is equal to an plus m. That's the second part, and say a naught is equal to b. Okay, so that's the recursive description or definition of the sequence. But we already did the legwork. We know the answer. Remember the formula. Or if you can derive it right now, so b plus m again, b plus m again. So after n steps, how much do I have?
100.
Well, no, I don't want to deal with the specifics right here. I want to take care of all the arithmetic progressions at once and know their limits once and for all. It will be b plus n times m. So starting point is b, and then I add m n times. Okay, so that's the sequence. And as you can see, you can guess what the pattern of the development into the infinity is, because the process is very simple. You keep adding. If you plot, you'll see like something like that. If you start plotting, it will be every time you progress, n progresses by 1. Okay, so n plus 1, n plus 2, n plus 2, and in the meantime, what happens to the value of the sequence every time you add m? Okay, so what can we say about the limit? It is infinity, indeed, but with one exception. exception. M could be 0. Right? In that case, the limit is B. Okay? So like I said, I want to take care of all the sequences, all the arithmetic progressions at once, and one of them is a trivial one. It is a constant sequence, just as what we discussed before. Another thing is the infinity. There are two infinities. So if we want to be careful, we want to say what the limit is. So the limit of an is plus infinity, or it could be minus infinity, depending on the sign of the of m. So if m is positive, you will end up at positive infinity. If m is less than 0, then you'll end up at negative infinity. Okay, so here we go. We have the analysis of all the arithmetic progressions. Let's do the next one was the geometric progression. And you start with say a naught is equal to b, and then multiply by say r every time. Then the recursive definition is, once again, a naught is equal to b, and an plus 1 is equal to what? You multiply by r every time, so it will be r times an. Okay? And then once again, what is the limit? If we keep multiplying, it's very much dependent on r. So let's assume to keep it simple, let's assume that b is not equal to 0, otherwise it's not going anywhere, right? So you don't want to multiply 0 by something and then try to guess what's happening. Of course it will be still 0. And we'll also assume that r is not equal to 0, but for the same reason. You don't want to end up at 0. I mean, it's just too simple. So suppose r is not equal to 0 and b is not equal to 0. So we keep multiplying by a number. So what is going to happen? Well, suppose, well, as a particular instance, what if r is equal to 2? Well, actually, we probably should just go back and remember the formula. What's the formula if you remember? The formula of an in terms of n. You multiply b by r n times. So what do I get? Repeated multiplication, exponent, yeah. So the repeated addition, it gives us multiplication. Repeated multiplication gives us the exponent, or power, or n. Okay. I'm not sure. Actually, I'm not sure which one of these formulas is more revealing in terms of the long-term pattern. So, I mean, we actually haven't studied exponential functions, certainly not in this course, to actually know what they behave like. Or maybe you do. You remember the exponential functions? Yeah. Yes. If they behave like this, if what? No, it has to be larger than 1. So if you multiply by 2, it will be double, 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 double every time. If you multiply by 1.01, it's still, so 1% interest rate, it still will be growing and will be growing to infinity. So, okay, so that's one case. Limit an is equal to infinity if r is larger than 1. In other words, it diverges. Diverges as we also add diverges to infinity. So that's the way to describe it. Algebraically, you just simply write it is equal to infinity. But then there is something left. Then we are left with the possibility that r is less than 1. So, for example, 1/2. You half and half and half and half, what do you get at the end?
Get closer to 0.
You're getting closer and closer to 0, right? So an is equal to 0 if r is between 0 and 1. And why do I do it this way? Because why do I exclude 0? We already excluded 0. Well, first of all, let's appreciate the outcome, that the limit exists. So, and the difference is crucial. The divergent behavior of the sequence when that ratio, this is often called the ratio. Well, this ratio is larger than 1. Well, actually, there's a case that I skip in between. So when it is r between 0 and 1, it is clear that you make it, you multiply by 0.99, it will be still getting smaller and smaller and smaller, and it will eventually reach 0. We can do it with the definition, epsilon, if we like. But I did skip one case in between, and that is r equal to 1. Well, if you keep multiplying by 1, then what?
It's going to equal b.
It will be equal to b. Okay, so limit an is equal to b if r is equal to 0. Okay, so that's supposed to be here, but then we still there's r is equal to 1. I'm sorry, r is equal to 0. We exclude, and then we still recognize that there is more, and that is when r is between -1 and 0. What do you think is going to happen? So in other words, we're multiplying by -1/2 every time. b -1/2 to the n.
It'll still go to 0.
It's yeah, it still goes to 0, right? Because that negative sign is really no big deal. This is what I would do with it: b -1 to n and 1 over 2n, like that. So you can see that -1 to the n simply alternate the sign, but the second part, 1 over 2n, grows, getting closer and closer to 0. So even though it will alternate, just the example we had last time, it will be eventually going towards 0. So in this manner. Okay. So the answer is still 0, and the last case remains, and when r is less than -1. Well, I'm sorry, I skipped r equal to 1 again. So r equal to 1, what's the answer? When r is equal to 1?
It's b.
Careful. You keep multiplying by -1 every time. So what is it?
Negative b. Positive and negative b.
You remember there can be only one limit. There is no limit, right? You can just write does not exist. This is a standard way to write it in calculus 1, DNE, meaning that does not exist. So this limit does not exist because the sequence becomes very simple. It is b, negative b, b, negative b, and we already know this cannot possibly converge to anything. So once again, keep in mind there can be only one limit. And it cannot simply go to two of them simultaneously. And the last case is when n goes to infinity and r is less than -1. So we're multiplying by r, say -2 as an example. Say r is equal to -2. So once again, this decomposition I did over here actually helps again. So you concentrate on the magnitude. The magnitude is increasing because you multiply by 2, but you also multiply by -1, which changes the sign. So imagine what's happening.
So it diverges to infinity or negative infinity.
Which, in other words, it simply diverges. It will behave in a very wild manner like this. So it not only it increases in magnitude or in absolute value, if you prefer, but it also swings between negative and positive. So we cannot even say this. This one right there was a pretty informative answer. It was n goes to infinity. It is something very very specific, and it is we could draw conclusions from that. This one, however, is the answer does not exist because there is no, not only there is no limit as a number, the limit is not even infinity. So that's the worst case scenario. These two is where they are not going anywhere at all, not even infinity. So that alternation, oscillation between two infinities guarantees that the answer is not infinity because it looks like there are two of them, one infinity or the other. It approaches simultaneously two infinities, which means that it's not approaching anything. Okay, so that's the conclusion. And well, one more example. I think powers. So n to, well, n could be with any power here, say, I'm sorry, Rn. Okay, so R is constant, and this is our index of the sequence. So this is An. It is, if you carefully pay attention, you can see the difference from this one. No, hold on a second. Upside down. No, I was right the first time around. So the power of n, and this is, say, x. So index is, this is the index, and this is the power, which is fixed. Okay, but we want to take care of all of them at the same time. Okay. So as an example, we could have, say, n squared. So x is equal to 1, you have n squared, x equal to 2 is n squared, x equal to 1, and we have n, and then you can have x equal to 3 and cubed. So where do these go? If n is increasing, what is happening to n squared? Okay, let's say take the first one. Where does n go as n goes to infinity?
Infinity.
That's right. If n goes to infinity, it goes to infinity. So, okay, that was easy. The second one, n goes to infinity, where does n squared go?
Infinity.
Also infinity, yeah. And all of them pretty much all go. The intermediate values also go to infinity, say n1 half, and so on. They all go to infinity. The slightly trickier one, what if I take 1 half? Square root of n. Where does square root of n go?
0.
No.
That still gets bigger, don't it?
It's getting still bigger. So it's like, what is it, square root of 2, square root of 4. It will still reach the highest point. It will be, every number is somebody's square root. So it will...
It'll just take longer to get there.
Yeah, exactly. So that's the difference in any kind of power. As long as the power is larger than 0, it will take you to infinity eventually. Okay, so where things starts to differ, it is when I pick x, say -1 half. Okay, and then x equal to -1. So 1 over n, 1 over square root of n. Okay, so that's where things are very, very different, because now n ends up in the denominator. So the denominator grows and it brings up the whole fraction. Which way?
Towards 0.
Towards 0, yeah. So x equal -2, same story. Okay, so let me just write out the answer in one place. So limit n power of x, n goes to infinity. There are 3 possibilities. 0 if x is less than 0. It is 1 if x is equal to 0, because, you know, there is no, it is equal to 1, the sequence is constant. N is equal to infinity plus infinity if x is larger than 0. Okay? So we start with the classification of the most basic sequences in terms of their limits. So we already know that which sequences are not going to be very useful Those are the divergent ones. So the number one task is then is to start with these basic sequences and then try to see what happens to limit as we carry out algebraic operations. So algebraic operations are first, before we get to limits, back to limits, let's see what we can do with sequences. So we can add two sequences term by term, producing a new sequence. Say an is equal to, say, 1 over n, bn is equal to 1 over square root of n. Okay? Plus 1. Why not? Okay, then define a new sequence. Cn is equal to an plus bn, or 1 over n plus 1 over square root of n plus 1. And whatever it is, you can simplify it or not simplify, it's a new sequence. Okay, so any algebraic operation you can think of will produce a new sequence. Okay, so rather than try to carry that's a very natural operation to carry out, really no challenge here. Let's jump straight to the question of what happens to the limit. Or the limits, because initially you have two sequences, each of them may or may not have a limit, and the question becomes what about the resulting sequence Cn? Any guesses? Well, let's take the specific sequence Cn. An, the limit is 0, bn, the limit is 1, and Cn, what's the limit of Cn?
0 plus 1.
0 plus 1. It is, in fact, the sum. Okay? And that's the idea, that at its simplest, when you have two sequences, convergent sequences, you conclude that their sum is also a sequence which is convergent, and the limit is equal to the sum of the limit. So it's called the sum rule. Okay, but first let me make sure that we are clear on its applicability. The sum rule, every time there will be more sum rules in the future, it is every time you have a limit, you have to ask yourself if you add things together, what happens to the limit? And the typical answer is that you just add them together. Okay, so this is the very beginning. So suppose, let me just state it, suppose Cn, well, let's say suppose a limit Cn is equal to C. I'm sorry, but what's C? I'm talking about An and Bn. An, limit is equal to A. The limit of Bn is equal to B. Then limit of An plus Bn is equal to A plus B. This is the short version. The short version of the sum rule, and the wide is the short version, even though it's fully applicable to the examples that we just had. You have sequences, you have their limits, you add them together, the sequences, and then you have to add the limits. Right? That's what has happened. You add the sequences right here. It means that you add limits. Okay, so far so good. The trouble is that what's missing in this shortened statement is that there is no discussion of convergence in the first place. So it's there, but it's hidden. So if you want to be careful, then you actually insert some statements, such as you say, A and B and converge to begin with. Okay, so you cannot discuss any limits unless you know that the two sequences converge, and then you conclude about the new sequence also the same thing. This new sequence also converges. Okay, so that's the parts of the theorem that always should be either written or at least kept in mind, that you have to assume to begin with that these two sequences converge. Otherwise, everything just is lost. Let me demonstrate, or let's work it out. Suppose, well, think about it. If A and diverges, then what? Then can what can you say about the sum? A_n plus B_n. Well, nothing really. Nothing. But if B_n diverges, if B_n, let's say B_n converges. So if A_n diverges, B_n converges. What can we say about the sum? And the answer is what? No, we could say, actually we can say it diverges. You can have an example of say in the above example you put up n over here. Oops, or n over here. Okay, so then B_n diverges, but B_n converges, A_n diverges. The sum is the fact that the second sequence behaves well actually does not means that we cannot discard or discount the fact that the first sequence runs away or oscillates wildly. So when the both sequences diverge, that's the weird thing. Then we cannot tell if both of them diverge. Turns out that we cannot conclude that A_n plus B_n diverges. So two divergent sequences not necessarily produce a divergent sequence. Can you think of an example?
Well, there is, remember how you have the divergent sequence before where it switched from 1 to -1 over and over again?
Yeah.
What if you had the opposite where it was -1
So
and switched to 1 and they match?
Okay, yeah, that works perfectly. So 1 is 1, -1, 1, -1. That's A_n. And B_n is the opposite, -1, 1, -1, 1. If you add these together, what do you have? A_n plus B_n, 0, 0, 0, 0, right? So they canceling each other. They canceling the bad part of the sequence. It disappears, and you're left with a constant sequence. So in other words, you take the negative of a divergent sequence, and they add them together, and you have 0. So that's what can happen. And pretty much that's one of the reasons why we stay away from divergent sequences, because when you carry out algebra with them, the results are unpredictable. The theorem, the sum rule, therefore, applies only to convergent sequences. Also, be careful about working backwards. But by that example we just had, which is very appropriate, not going backwards. So that word then is crucial, because it separates the conclusion of the hypothesis of the theorem from its conclusion. The hypothesis, the assumption, is that the two sequences converge, and the conclusion is that their sum also converges. Okay, so we cannot go backwards. We cannot assume that, based on this theorem, that the sum of the sequence is convergent, then the two parts it's made of is also convergent, which is that example indicates, right? So think about it. We take this one is convergent, and we realize that we cannot conclude from this that where that sequence came from, these two sequences are also convergent. They could be divergent. So once again, it is one side one-way street from two sequences added together to their sum, not backwards. Okay. All right, so that's not too bad. How about subtraction? Same story. Really no change whatsoever if I replace addition with subtraction. So I put a minus here. What's the difference? None whatsoever. And all the analysis that we have had would be fully applicable. The next operation is not, there are four algebraic operations. The multiplication of sequences works out just fine in the exact same manner, but there is a simpler property that usually is considered first, and that it is called the constant multiple rule. Okay, so this way we are combining a sequence with a number. So suppose AN converges to, say, L, and C is a number, any number. Then we can form a new sequence, C times AN, and it's also convergent. Converges, and you can guess that it converges to C times L. Okay, so once again, nothing bad that can happen. You just multiply by a number, including 0, and you have a new sequence, and the result is convergence towards the same number. It is probably, so I don't want to have too many examples of this kind before theorems of this kind before at one time. So I want to let's try to illustrate this with I don't know. Wait a minute. This one. So what we can do with sequences, let's illustrate these two algebraic operations with Excel. Okay, so we will give some of that, so we could have two sequences side by side. Let's just illustrate these algebraic operations on sequences, and then see that they indeed the limits also behave in a manner predictable. So let me do this from scratch. So once again, I'm starting with, I will have here n and a sub n here. These will be the two for sequence. The second sequence n and bn, and then over here I'll have n and an plus bn. Okay, bn. Okay, so let's pick sequences that we like. Well, let's start with n. So we start with 0. This one is equal to this thing plus 1. Okay, we can certainly spread it down, or do it later. No, not like this. Not like. Okay, like it's this. As I mentioned, there is a problem with the computer. Okay, so how about I take 1 over n here? How about 2 over n? Why not? So equal 2 divided by, I should have started with 1. I don't want to do division by 0, frankly. Okay, so this one equal to 2 divided by n. Okay, so that is my sequence. There are numbers. Okay, so I take this. It's not working. And I'll just put n where it belongs twice. Okay. Bn, so suggest a sequence. What sequence would you like us to have here?
10n.
10n?
2n.
2n. That's fine. Okay. These are the These are the rest of the elements. Then this is how I compute it. This is not a function of n anymore. I will compute this based on the previous two sequences. So the first element is this, and I add that. Okay. So that's how I add sequences. Very, very simply, row by row. So the first element, the first entry in that column plus the first entry in the column Bn, I have the result. Okay. That's my sequence. Okay. At this point, I could plot easily the. Well, let me do it this way. I can plot the. If the outcome is not clear, maybe it is clear already, but I plot it anyway. I'll plot the sequences. Okay, that is the first sequence. Well, that maybe. Now let's do the second sequence. Where is that? Insert. That's the second sequence. See how different it is, right? That's Bn, A and Bn. And now the sum, do it this way. Hold on, where is it? Okay. And this is the sum. Okay, so any observations that you would like to make?
Slight curve at the beginning.
Slight curve in the beginning, but as we don't care what's happening in the beginning, we only care what's happening at the end. So what's the conclusion? The first sequence, what about the first one?
It's going to zero.
We're going to zero. The second one?
Going to infinity.
Yes, and the last one?
Going to infinity.
Also to infinity. Okay, so that doesn't really fit. I mean, the behavior is clear, but it doesn't really tell us anything about the. It really is not about the application of the sum rule. Nothing wrong with this. This is just a good illustration of what can happen with sequences, and that's what I want to do. How about I take the second sequence and do something nastier with it? How about I put a sign of this? Sine of n. Sine n. This is my sequence. Sine n. What happened? Okay, I don't have enough n's, so I suppose I need to spread it like this. Okay. See the sequence? What happens to the sequence? So it alternates between it alternates in a random manner between -1 and 1. Okay, and when we add well-behaved sequence on left to the poorly behaved sequence on right, even though it does not go to infinity this time, the outcome is still very nasty. It is still not. It's not going to converge to anything. Okay, so but if we were to multiply it, what do you think is going to happen if I, instead of adding these two, I multiply them?
It's going to go to zero.
It will go to zero. Let me demonstrate. So I will replace this plus sign over here with multiplication. Okay. And let me spread it down and some more. Okay. Well, numbers speak for themselves. The picture is even more revealing. As you can see, it oscillates in a kind of in a random manner, but at the same time, the swing decreases. The swing decreases in that it appears to converge to zero, even though I wish I could. For some reason, it's converging kind of slowly. Why is it? I thought I had enough elements here.
You don't have enough of the
Data? I don't have data. I thought I did. Let's do it this way. Okay, let me just a minute. Select data. Okay, so just this way. So it becomes literally 0, even though as you can see, Bn contributes this randomness to the sequence. It is actually the first sequence, An shrinks it to harder and harder to 0. So the more elements you have, it becomes literally a straight line. Okay, so we'll just resume tomorrow, and hopefully I will assign the next homework tomorrow. Okay.